Okay, does anyone have questions from the homework? Yay. No questions from the homework? I cannot see anybody. If anyone would like to turn their camera on. Oh, thank you. Awesome. Hi, Jasmine. Hi, Mia. This is amazing. I always wonder which two people will I get to teach at tonight. All right. Awesome. All right. So we got Karen. Hi. Does anyone have questions from the homework? Hi, Brandon. Oh, we got Nancy. Let's see. Beth will probably turn on her camera. Oh, this will be great. Okay. All right. Well, if we don't have questions from the homework, then I'm going to finish this chapter out. Just a reminder, you have a test on Monday, and it's going to cover 3.1 through 3.5. I'm not going to do 3.6, 3.7. It's not a big deal. You won't miss them. We don't have time for them. So, it's you kind of get used to pacing things in the classroom, and you kind of get used to knowing how things are going to go, and everything's different online. So it's all a learning process. Last time when we were talking about 3.5, we were discussing the domain for a rational function. Well, we talked about what a rational function is. It's the quotient of two polynomials. And then we talked about how to find the domain of a rational function. Angel, no, we have a test Monday, not today. Let's see. Most of our tests are Mondays, not Wednesdays. Were you all prepared for your test today, Angel? Yeah, October 12th. It's on the syllabus. I mean, for the most part, we're going to stick with this. My gut tells me that test 3 is going to move. Very likely it's going to have to move because we have to cover all the chapter 4 topics. So test 3, I would imagine, will move. But test 2 is right on schedule. They changed Google Meet, by the way. They added breakout rooms. And the chat looks different. Weird. Okay. All right. So we talked about how to find the domain of a rational function. Does it look different for you guys? Maybe it looks the same. Okay. So to find the domain of a rational function, we're going to exclude any values for which the denominator is 0. Now we're going to use this idea along with the definition for a vertical asymptote, and then we're going to talk about how to find a vertical asymptote for a rational function. Now, we did not have to worry about vertical asymptotes for polynomial functions because remember that polynomial functions were continuous. We could graph them without ever having to lift up our pencil. The big difference between a polynomial and a rational function is that a lot of times rational functions will have these asymptotes in them. So asymptotes are basically breaks in the graph. If you can imagine your graph will kind of follow the behavior of an asymptote. So an asymptote is basically just this vertical line that kind of runs through somewhere in your function. And then your function kind of has to just follow along with this invisible line. So asymptotes are going to be breaks in the graph. And we're also going to talk about how to tell the difference between an asymptote and a hole. So sometimes it'll look like everything is smooth and continuous in your graph, but it's really not because you'll have a little hole in your graph. So we're going to talk about how to identify these discontinuous features in our rational functions. First, we're going to focus on finding vertical asymptotes. We're going to talk about how to use arrow notation. We'll do that on the next page. But for now, the line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches a. So you don't know, you kind of have to figure out by checking some values whether your function's increasing or decreasing as it approaches that asymptote, but it will do so without bound. If you have a rational function in which p and q have no common factors, that's a key here. and a is a 0 of q of x, then the denominator, then x equals a is a vertical asymptote of the graph. So if the two polynomials that make up your rational function have no common factors, then you can just take your denominator, set it equal to 0, and whatever values you get, x equals that value will be a vertical asymptote. This definition does not apply if you do have common factors between p and q. So if you can factor it and you end up having common factors where you can cancel one out, you'll still have a discontinuity there, but in that case, we'll talk about the graph having a hole at that point, not an asymptote. And you'll see the difference between these two as we work our way through. So the arrow notation we're going to be looking at, and this might be new to you, probably is new to you. We're going to talk about x approaching a from the right. So when you see this plus sign, it looks like it's in an exponent for a. That means that your value x is approaching a specific value a from the right. Sometimes this is confusing to students because when you're thinking from the right, you're not heading in the direction of right, you're heading left. So if you're heading from the right, you're actually heading left. So make sure we understand the difference there. Now, if x approaches a from the left, we're going to denote that by putting that minus sign in the exponent of a. Now, you can use the same type of notation to note that x is approaching infinity or x is approaching negative infinity. So you can see what this looks like on the graphs. Now, this first example shows as x approaches a from the right, f of x approaches infinity. So we're going to need to use this notation. You're going to have some homework problems that do use it. But as x approaches a, now a is just this value x equals a, wherever you are on this line. As your value of x approaches a from the right, means that I'm coming from the right and heading towards the left. Then the value of f of x, which is the value of y, heads all the way up to positive infinity. It has nowhere else to go. You cannot cross a vertical asymptote. So you can't have the situation where all of a sudden your graph is going to go boop and then come back over again. It can't do that. All it can do is slowly approach x equals a and just get infinitesimally close to a, but never actually reach a. By the way, this asymptote is showing up in a dotted line because it's not actually a line on your graph. It's a function. You cannot have vertical lines in your function. So your asymptotes are always going to show up with these dotted lines. Contrast this with x approaching a from the left. So if x is approaching a from the left, we're approaching on our function from the left, which means we're heading to the right. We're approaching these values of x equals a. We're not going to reach them, but we're going to get closer and closer and closer. And as we do, the values of f of x will go up and up and up and up forever, all the way up to infinity. Let's see. You can see similar behavior if you have the values of f of x heading downward. So as x approaches a from the right, in this case, f of x is heading down. So that means f of x is approaching negative infinity. And then in this last example, as x approaches a from the left, f of x approaches negative infinity. For some people, this comes very easily, and for others, they really need to practice using this notation. So you will have a couple of homework problems using it so that you make sure you know what that means. Does anybody have a question on the arrow notation? No. Okay. Wonderful. All right, so number 3, use the graph of the rational function shown to complete the statement. As x approaches 2 from the left, f of x approaches what value? So we're going to look at the graph and figure out as we approach 2 from the left, what value does f of x approach? Now, notice that on your graph, we don't actually have an asymptote shown at 2, but if you find it helpful to graph that vertical dotted line through x equals 2, that's fine. Do that. Whatever makes it easier for you to see this. I'm trying not to hit my function here. I also want you to be really careful here because x is approaching 2 from the left. Sometimes people see this minus sign up here and your brain does something where you're thinking -2, but you're not actually approaching -2. You're approaching 2 from the left. So make sure you understand that we're looking at x equals +2 and not -2. Okay, so as x approaches 2 from the left, what you're going to do is you're going to follow your function and you're going to approach 2 from the left. So your graph, your x values are getting closer and closer to 2. I know it doesn't look like it because you're thinking about y values. Don't think about y values. Just look at your x values. So as you're approaching 2 from the left, you're heading down this function. It looks like a parabola in the middle. And then as you approach 2 from the left, your x values will get closer and closer to 2, and your y values will get larger and larger and larger and larger. So because of that, we would say that as x approaches 2 from the left, then f of x will approach +infinity because the values of f of x will go up without bound. Now, just for good measure, we can, if you would like, add an additional piece to this and talk about what happens as x approaches 2 from the right, just so we understand the difference. So as x approaches 2 from the right, we're looking at values of x that are greater than 2. And notice here we're heading towards 2, and as x gets closer and closer to 2 from the right, the values of f of x are going to go down without bound. That means that the values of f of x will head towards -infinity. So we can say that as x approaches -2 from the right, f of x will approach -infinity. We could do something similar at -2, but we kind of saw both things occurring here at 2. Does anybody have a question about this example? Okay. All right. Wonderful. Let's do another one. As x approaches infinity, f of x approaches what value? This one's a little bit trickier. This one is actually leading you to talk about end behavior of the function, or really a horizontal asymptote, which we'll come to. But as x approaches infinity, you're looking at values of x that get increasingly large, so all the way out to the end behavior. Now, you only know so much about what's happening on this graph, but you can see that you had these values of f of x that started up higher, and then as x increased, they got lower. Now, what's actually going to happen here is these are going to level out. And this question's a little difficult, I guess, just because it's kind of hard to tell exactly what's occurring here. But what you actually have is this horizontal asymptote at 1. And you might be wondering, well, how do you know that it's approaching 1 and not 0? Yeah. If I were to give you something like this on a test, it would be a little bit clearer. It would be a lot clearer. But in this case, let's go ahead and draw our dotted line for the horizontal asymptote at y equals 1. So in this case, we can say that as x gets really, really, really large, f of x, or the value of y, is just going to head towards 1. Y equals 1. And we will discuss horizontal asymptotes here in a couple minutes, but we've now used the arrow notation with the vertical and the horizontal asymptote. Are there any questions on these examples? Okay. Wonderful. All right, so now let's talk about finding vertical asymptotes. We talked a little bit about this already. What we're looking for here are values where the denominator could possibly be equal to 0. But we want to make sure there's nothing that we can cancel out first. So we're going to double check for that. If we mark it as 1 to the, do you mean like 1 from the right, Angel? Sorry, he's asking a question in the chat. Yeah, because officially it's just approaching Oh, I see what you mean, like one from the top instead of like one from the bottom. I think that's what you're talking about here. Yeah, you can just say it approaches 1 because it does not matter which direction it's approaching from when we're talking about the value of f of x. It just matters that we're approaching a particular value. Does that make sense? Okay. Yeah, so you can just say 1. Okay, let's see. Looking at this function, g of x equals, in the numerator, x plus 1. In the denominator, we have x times x minus 1. Whatever you do, don't do this. Don't do that. You cannot cancel between terms. Even though, yes, technically you have a factor of x here in the denominator, you don't actually have a factor of x factored out in the numerator. These are terms. You cannot do that. So don't say, oh, cool, I canceled something out. Now I've simplified things. No, you have not, because you've done something wrong. You cannot cancel between terms. In this case, if there's nothing that you can cancel out, then you're just going to start looking at your denominator. And both of the values that would make your denominator 0 are going to become vertical asymptotes on your graph. So in this case, set your denominator equal to 0, and then use that 0 factor property to find the 2 values that will be asymptotes on your graph. So we have x equals 0 and x equals 1. Vertical asymptotes are always written in the form of x equals. They are equations of lines that are vertical. So when you are listing your vertical asymptotes, the directions on MyMathLab underneath the answer box will say type an equation. That means type something in the form of x equals when you're writing in a vertical asymptote. And that's it. And if you'd like to see, if you're like, wait a second, I don't believe you, this looks funny, look at it on the graph and see what happens. Now I have to, oh wait, will this actually work in this light? Maybe. Let's see. You can graph this function. We need more practice with this anyway. Yeah, it's like thinking about working properly. I might have to turn the light on and see if that helps. X minus 1 in parentheses. It must, if you've got 2 terms in the numerator, it must be in parentheses. In the denominator, you have x times x minus 1. I probably have an extra set of parentheses I don't need, but that's okay. Might as well do this now. That's better. No, worse, better. That might be might be about as good as it gets. Okay, go ahead and graph this. Benjamin says, when I use my calculator, I get dim mismatch. I wonder if you have your stat plots on. Karen, was that what you were getting when you had emailed me the other day saying your calculator was giving you an error? Was it a dimension mismatch thing? Make sure Karen's on here. She was here. Yes. Okay. So that's a really common problem. And I think it's because a lot of people take stats before they take this class. They take like 102 or something. So their calculators are set into a mode they used in stats. If you get something like that, go into your stat plots, which is second y equals, and make sure your stat plots are off. Because a lot of times when students have this problem, they ask me to look at their calculator and their plots will be on instead of off. So if you hit enter, you can toggle from on to off and then go back. Did that fix it, Ben? Awesome. Okay. You're welcome. I hope this makes your life easier today. So you should be getting a graph that looks like this. I still am waiting to hear back on this emulator. I should bug them about it. There might be a way. Oh, I doubt it. What if I picked something weird? No, terrible. No. Maybe. We need to find a way. Terrible. I don't know. That's about as good as it was before, I guess. All right. Do the tilt thing again. You can kind of see here that you end up with these big breaks in the graph where you cannot connect them at all without, you'll never be able to connect them. The breaks occur at 1 and 0. Your asymptote is not actually going to be graphed on your graph. If you have a really old TI, you might actually have what appears to be a vertical line on your graph. It's not actually vertical. I've seen that happen sometimes, that back when I had my old TI 83. But you're seeing this huge break at 0, and then you're seeing another huge break at 1. And if you are like, wait a second, how do I know they're occurring at 0 and 1? We'll go back to your table. If you're still set to ask like you were the other day, you can just enter 0 and 1. Otherwise, if you're set to auto, you should have those showing up in your table anyway. I'm getting errors at 0 and 1. That's because we can't divide by 0. That's how you'll know, wait, this has to be some sort of issue with the domain of our function. Does anyone have a question about this graph or the asymptotes or your calculator in general having issues? Okay, because if your calculator is also having an issue and you don't want to ask me in class, feel free to stick around for the office hour and we'll see if we can get it figured out. Okay, so that's what an asymptote will look like on your graph. Also, you can kind of see the asymptotes. We have 2 of them in this function, and then there are 2 vertical asymptotes over here. So kind of gives you an idea of what they look like. Okay, now, number 5 is very different from number 4. You'll be thinking, oh, no big deal, looks the same. No, it's not the same. With number 5, you can rewrite this, and you must rewrite it, where the denominator is factored as the difference of 2 squares. X squared minus 4 is x plus 2 times x minus 2. This is an extremely important step. If you don't rewrite this, then you're not going to know that you have common factors between the numerator and the denominator. X plus 2 and x plus 2 are common factors in this case. You can't cancel just the x, but x plus 2 as a whole, you can cancel. So x plus 2 and x plus 2 cancel out. That does not leave you with 0 in the numerator. Remember, a quantity divided by itself is 1 over 1. So this just leaves you with 1 divided by x minus 2. Now, that doesn't mean that the domain problem that occurred with this factor is no longer a problem. It just means that we've now written this into an equivalent form. We were able to get rid of one of those issues in the graph to figure out which one of these values was a vertical asymptote. X minus 2 equals 0. X equals 2. We need to talk about this other value and what it meant to our graph. Clearly, there's a domain problem when you let x equal -2. -2 plus 2 is 0. But now it looks like it's not a problem. It still is a problem. This was not our original function. 1 over x minus 2 was not the original. Our original included this value of x plus 2 in the denominator. If there is a value that was excluded from your domain, but you were able to cancel it out, that value does not become a vertical asymptote. It becomes a hole in your graph. So on your homework, you're going to be asked to look at a function, determine any vertical asymptotes on the function, and determine any places where your graph is going to have a hole. Now, the big difference between a vertical asymptote and a hole is that a vertical asymptote is this giant break in your graph where there's no way that you can connect the ends. Either both ends are going all the way down, they're never going to meet, or one's going up and one's going down. It's a huge break in your graph. It's infinitely discontinuous. A hole would just be like, you can barely even see it. It looks like your graph would be continuous, except it's almost like a student once described it to me as a pothole in the road. You're driving along the road, you hit a pothole, and then you keep going again. So that's kind of what a hole looks like. So we can also look at that on our graphing calculators. So we are going to graph the original function. Our original function was, in parentheses, x plus 2 divided by, also in parentheses, x squared minus 4. Now, when you graph this, you're going to see that huge discontinuity at 2. The hole at x equals negative 2, you're not even going to notice. You're not even going to see it. It's going to look like it's not even there. Even if you zoom in really, really close, with some functions, your graphing calculator, if you zoom in super close, will actually show like a tiny like pixel missing, but it's kind of hard to get it to do that. Go to your table and let x be 2. That was your asymptote. You get an error. Let x be negative 2. That was your hole. You still get an error. You just don't see it appearing the same way on your graph. Now, if you were to graph the equivalent function, which is f of x equals 1 over x minus 2, you would see that that function's exactly the same. It just doesn't have the hole in it. So if you go back to your y equals and you graph 1 divided by, in parentheses, x minus 2, which was the equivalent function, you can graph it. It's just going to graph right over your original. The only difference is now when you go to your table, you don't see that hole at x equals negative 2. You actually get a value there. You still have the vertical asymptote. You don't have the hole. Other than that, they look exactly the same. So you're going to use this skill a lot in calc also, just kind of reducing this down to an equivalent form that doesn't have the holes in it. But it is important. We do need to note it. Does anybody have a question there? Okay. Let me check my chat. It used to tell me how many messages were in the chat, and now it does not. So that was vertical asymptotes. Now we're going to talk about horizontal asymptotes. And if you take calculus, you will talk about these again as limits at infinity. And your teacher is going to remind you that you already know the rules for finding these. All right, so we kind of talked about a horizontal asymptote on the previous page. We were talking about what happens to the value of f of x as x gets increasingly large, or I guess we could also consider it being increasingly small in the other direction. That is how we would define a horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. So you're seeing this arrow notation again here. As x approaches infinity, that means if you look to the way right of the graph, f of x is approaching y equals b. So your function is approaching the value of b. It could happen that it approaches b from the top. And this, I guess, kind of brings me back to Angel's question. When you are specifying the value for the horizontal asymptote, it does not matter if you're approaching b from the bottom or from the top. The only reason we use that plus or minus notation is so that you can figure out what direction the function is heading in as you approach a certain x value from a particular direction. But once you figure out what that direction is, it doesn't matter how you're getting there. All right, so we can approach b as x gets increasingly large, also heading in this direction. So you could see similar behavior where we still have a horizontal asymptote at b. just heading from the other direction. Now, I mentioned something before about how you can never cross a vertical asymptote. That's true. It's a function. If it crossed a vertical asymptote, you'd fail the vertical line test. It wouldn't be a function anymore. Sometimes students get confused by the fact that a horizontal asymptote can be crossed by your graph. What I want you to remember is that a horizontal asymptote really is just talking about the end behavior of the function. So what value does y eventually approach as x gets increasingly large or small? If your graph ever crosses a horizontal asymptote, it won't do it at the end. It'll do it somewhere here in the middle. It can happen. It doesn't happen a lot, but it does happen. And I don't want you to think, wait, I must have done something wrong. I can't cross a horizontal asymptote. That's not true. You can cross a horizontal asymptote. It's just not going to happen at the ends. So I think we're going to also graph one where this happens, where you're going to see that the horizontal asymptote is actually going to get crossed in the middle. But remember, it's dictating the behavior as x gets increasingly large or increasingly small. So you'll see some pictures of that. Are there any questions so far? Okay. Locating horizontal asymptotes. Now, you're going to have your notes with you when you're taking your exam. So officially, whether or not you remember this is totally up to you. I have kind of a shortcut that I always use to remember horizontal asymptotes. I think it's really helpful, and it's a great shortcut because someone taught it to me when I was a TA at NIU years ago, and I was a TA for a college algebra class when I was in grad school. And one of the other TAs was like, oh, have you seen that trick to figure out the horizontal asymptotes? And I hadn't seen it, but she showed it to me, and I never forgot it. So I will show it to you today, and hopefully, for if you take calc, it'll stick with you, and you won't feel like you have to remember this all the time, because this will pop up again for you in Calc 1 and in Calc 2. All right, so let's say you have f of x, this rational function. All of your function of degree n is in the numerator and degree m is in the denominator. If the degree of the numerator is less than the degree of the denominator, the x-axis, or y = 0, is the horizontal asymptote of the graph of f. So if you have a hard time seeing this, remember that n is the degree of the numerator. And m is the degree of the denominator. I don't usually drink coffee at 6:30 p.m., but that debate is coming on tonight, and it's going to be a late one for me. Gotta be caffeinated. You guys excited for the debate? Yes. Not at all? No. Oh, I shouldn't have asked because I wasn't prepared for responses of no. Well, I'm really excited because my children are half Indian, and Kamala Harris is half Indian. I think it's really exciting. We're very excited. It'll be a good debate. I remember the last VP debate 4 years ago. It'll be a good one.
She's a bad person.
That's just like your opinion, man. Husband reveal. What about my husband? Oh, that he's Indian? Yeah, it's true. 4 years ago was different. I know. You guys on the chat are something else. Okay. Here we go. Horizontal asymptotes. Let's continue with our definition. Little segue there from the VP debate. I'm just so excited about it. If n equals m, the line y equals a sub n over b sub m is the horizontal asymptote of the graph of f. Now, this is a fancy way of saying that your horizontal asymptote is y equals the ratio of the lead coefficients. Let's rewrite this. All right. The other scenario we're going to have will occur when n is greater than m. So the graph of f is going to have no horizontal asymptote in that case. Now, you have the notes, you have the definition. The way that I like to remember this is by filling out sort of the way that I remember it is kind of filling out a placeholder to determine your horizontal asymptote. So if you're thinking about a case where n is less than m, so the degree of the numerator is less than the degree of the denominator. If that was the case, then you would have something like, let me write an example here. The degree of the numerator is less than the degree of the denominator. Something like 3x divided by 5x squared plus 1. Now, the way that I remember this is I'm just going to fill out a placeholder in the numerator to cover that power that you don't see. So in the denominator, you have 5x squared. Make your numerator also second degree, but it's going to have a coefficient of 0. So we'll call this 0x squared plus 3x divided by 5x squared plus 1. Now, if you want to always use the rule for number 2, then by the rule for number 2, your horizontal asymptote is y equals the ratio of the lead coefficients. So y would equal 0 divided by 5, which is just 0. Wow, I really ran out of space here. Well, hopefully we know 0 divided by 5 is 0 because I only have half of a 0. Here, I'll just try not to move my page. There you go. And that's exactly what this rule says for number 1. If n is less than m, then y equals 0 is the horizontal asymptote of the graph. What is half? Oh, well, half of 0 is just 0, but I just meant that I had only drawn half of a 0, so I put the other half here. And you will have forgotten about it in a minute, so when my page moves, no big deal. Okay. In order to use this rule, though, you have to remember that 0 divided by a real number is 0, and that a real number divided by 0 is undefined. All right, so number 2, an example of that would be something like 3x squared over 5x squared plus 1. So if you had such an instance, then the horizontal asymptote would be y equals 3 over 5. Now, in this case, I didn't need a placeholder because the degree of the numerator and the degree of the denominator were the same. The other instance that you might see would be for case 3. And such an example might be 3x squared divided by 5x plus 1. In this case, the degree of the numerator is greater than the degree of the denominator. And you can use the same trick that we used for case 1 here. You could say that this is really the same as 3x squared divided by 0x squared plus 5x plus 1. And as long as you give the numerator and the denominator the same degree, then you would say that y would equal the ratio of the lead coefficients, which is 3 over 0. And that cannot be. We cannot divide by 0. So it must be the case that there is no horizontal asymptote. There is no horizontal asymptote. I am never going to write out horizontal asymptote. I'm going to call it HA. Okay, so you always have these rules to fall back on, but if you're working through your homework and you're kind of like, all right, I don't really feel like I need to keep looking at these rules and really analyzing it, just think about it this way. Just mentally in your mind, pop a 0 in the numerator or the denominator, wherever it needs to go. And then you can figure it out. Use it if you'd like. You don't have to. You can just follow the rule if you want. I found this to be helpful because it helped me to always remember without looking at the definition, because I could never remember, wait, which one is it? If the numerator of this is that, this or that, I couldn't remember. I always had to look. All right, find the horizontal asymptote, if any, of the graph of the rational function. So for number 6, in this case, you have a situation where the degree of the denominator is greater than the degree of the numerator. So if you're using my trick, make the degrees the same by using a placeholder, in this case, in the numerator. And then you would get a horizontal asymptote of y equals 0 over 2, which is just y equals 0. B. So once you get the hang of this, you will find that it is super straightforward. One thing I will caution you to is make sure that your numerator and denominator are both in descending order. You would hate for your lead coefficient to not be the first coefficient, and then you're like, whoa, hold on, I based everything off the first coefficient, but it wasn't the lead coefficient. For number 7, y is the ratio of the lead coefficients. You already have the same degree in the numerator and the denominator. As long as that's the case, you can go ahead and write your horizontal asymptote as y equals the ratio of the lead coefficients. And just in the same way that we would write a vertical asymptote using x equals for the equation of a vertical line, for the equation of a horizontal asymptote, we always will write y equals, and then whatever that asymptote is, always in the form of an equation. So that one would be A. Now for number 8, again, I would put a placeholder in here just because I don't want to have to look back up at the definition. And when I give the numerator and the denominator the same degree, I'm going to end up with a 0 in the denominator. And I know that we cannot divide by 0. So that must mean that we have no horizontal asymptote. I think there was some song from the 80s called Divide by Zero. Does anyone know that song? No. It's probably not a very good song. Are there any questions on horizontal asymptotes? Okay, your basic reciprocal function graphs are given to you on the next page right here. One of them you're going to use a lot. That function is 1 over x. Actually, we didn't discuss this in chapter 2. I thought we had discussed it, but you know what? Maybe we didn't talk about 1 over x. Yeah, we did not actually. This is your reciprocal function. It's called a reciprocal function because you always get a reciprocal by switching the numerator and the denominator. Or I'm sorry, yes, switching the numerator and the denominator, I guess, in most cases. Your reciprocal function is 1 over x. Now, your reciprocal function has a vertical asymptote at 0, x equals 0. because clearly 0 would make your denominator 0 in that case. It's not in the domain. So you have this vertical asymptote heading through your graph that's sitting on your y-axis. And you also have a horizontal asymptote at 0 because the degree of the numerator is less than the degree of the denominator. So you have a horizontal asymptote at y = 0. So what you have here for this reciprocal function are just an x value like 1/2 and the y value that is its reciprocal. So you're seeing that occur throughout your graph. So 1/2 and 2, 2 1/2. You would also, of course, have 3, 1/3, 4, 1/4. You just see this behavior occurring. So clearly, as x gets larger, y would get smaller because you're continually dividing by a larger number. Same idea as you head up towards y = 0 as x gets increasingly small. Let's see. Oh yeah, your basic reciprocal function is odd. Remember that an odd function can be seen by flipping over the graph and verifying that it looks exactly the same as it did before. So we have that behavior here. An odd function has origin symmetry. The other function that we're going to talk about in this section is f of x = 1/x². That one looks like this. You do have still a vertical asymptote at x = 0, and you also have that horizontal asymptote at y = 0. However, the behavior of the graph is different. You've got both of these with y values that are only going to be positive, which makes sense because you're squaring all of the x values that you enter. So your y values can't be negative. It's not going to happen. But you're seeing similar behavior. This time you're taking the reciprocal, but you're squaring in the denominator. So these values are going to get smaller even more rapidly than they did in this basic reciprocal function. The function 1/x² is even. That means it's symmetric about the y-axis. That, remember, means that you can flip it over the y-axis and you'll see the same thing. We have the y-axis symmetry there. An even function means f of -x = f of x. And then your odd function means -f of x = f of -x. So I don't want to dwell too much on these basic functions because, I mean, you will have them right here at your disposal. But it's, I think, a good practice to use the transformations that we talked about in 2.5 to graph these reciprocal functions, since we did not talk about them in 2.5. So if you remember back in 2.5, we talked about what happens when you subtract a value off the function or subtract a value inside the function. In this case, we're not going to take your function down 5 units. Remember that if we were to shift it down 5 units, we would have 1/x minus 5 would be on the outside of the function. In this case, you have x minus 5, where the -5 is inside your function because it's actually in that denominator. So this would be your function, f of x = 1/x shifted, what do we think? 5 units, which direction? Oh, sorry, Angel just said to the right. You know, every time I have the chat selected, it doesn't beep. That's why I always have to unselect it. Yes, you're right. It is shifted to the right 5 units. It's to the right because the subtraction is happening inside the function. And remember, when it's inside the function, we'll do the opposite. We don't want to think left when we see a minus sign. We want to think right. So you're talking about taking your basic reciprocal function and all of your points are going to move 5 units to the right. That means that your vertical asymptote is also going to move 5 units to the right. So it used to be at x = 0. Now it's going to be at x = 5. Now, officially, you're just using transformations to graph these points. You originally had a point at 1, 1. If you're considering that your origin is basically moving over here to 5, 0, then you can put 1, 1 at 6, 1, Remember, all we're doing is we're just increasing each x coordinate by 5. The y coordinates are staying the same. The function's not moving up or down. So we used to have a point at 2, 1/2. We'll add 5 to the x coordinate, and that will get you to 7, 1/2. And then you can just kind of see how this function has this behavior where it increasingly approaches the x-axis. We also had the behavior where we were increasingly approaching this vertical asymptote. So this is 1/2 of your graph. Try not to touch the asymptote. Just make your graph look like it's approaching the asymptote. And then because we have origin symmetry, we can go ahead and repeat that exact same behavior down here in what used to be quadrant 3. Now we're just talking about values that are less than 5. And you already know what it's going to do. You don't have to sit here and graph every point. As long as you put an arrow on the graph indicating its behavior, that's all you need to do. You don't have to run it all the way out and complete all of the whole axis. Just my function's kind of bothering me because it almost looks like it's heading down a little bit. It should always be approaching the asymptote all the time. I sometimes see students who turn in reciprocal functions that look like this. Don't do that. It should not look like it's heading down. You should always be approaching your asymptotes. In order to approach the asymptote, see, now I'm too close. Sometimes it's hard to graph with asymptotes because you want to approach them, but you don't want to get too close. Do the best you can. Okay. Questions on number 9? Wonderful. Now I'm going to leave this kind of underneath here because we're going to use it for number 10. This is your other reciprocal function for 1 over x squared. This time we have a -2. So that was probably our most straightforward transformation. That just means you're shifting your graph down 2 units. So if you're thinking about where the original graph had its vertical and horizontal asymptotes, we still are going to have a vertical asymptote at x equals 0, but the horizontal asymptote is going to shift down 2 units. So it's no longer going to be at y equals 0. It's going to be at y equals 2. So denote that with a dotted line. Try to make it as straight as you can. I should have gotten a straight edge, but I did not. And then just copy those points down. Now, if you shift it down 2 units, the x coordinates are not going to change. The y coordinates are going to decrease by 2. So looking at your original function, you had a point at 1, 1. Well, now you're going to have a point at 1, -1. So everything is just going to shift down. And then you don't have to copy every point. Just, get me a general shape. Show that you are approaching the asymptotes. I'm not going to get too crazy about these. You can always check the points if you're not sure if it looks funny. But this is the behavior that we're talking about when your graph is approaching asymptotes. So I'm trying to model good behavior here where we're approaching the asymptotes, not touching them. Questions on number 10? Okay, so now we're going to graph rational functions. I'm actually going to include an extra example of this because I wished I had placed it differently. That's part of the problem with having to mail you all notes in advance. Is if I wanted to change something, I can't just, say, oh, I'll change it and then bring it to the copy center before class. Everybody's got it. So I am going to add an additional example here because I want to make sure that we are pretty clear on how to graph these rational functions. It is a big deal. By the way, I do have some homework up for you for graphing by hand. I believe it's going to release at like 7:40 or something tonight. The assignments on D2L, I'm not going to email you this time unless I really feel like I need to, but you will have some graphing by hand homework. It's on D2L, so if you are on D2L, you should be getting some sort of notification that's saying, you know, you have this and it's going to be due soon. But it'll be due on Monday. I really want you to practice this because you're going to have to graph a rational function by hand on your test on Monday. And graphing rational functions on my math lab is not the same when you're choosing multiple choice versus actually having to graph these by hand, which you're going to have to do for your exam. So that's why I want you to practice doing these without choosing multiple choice answers. Those are just really easy to eyeball and check with your graphing calculator. Not the same skill. Okay, graph rational functions. The following strategy can be used to graph f of x equals p over q, where p and q are polynomial functions with no common factors. Determine whether the graph of f has symmetry. I always tell students that it's really helpful. I usually don't require you to check for symmetry on an exam, but it can make a huge difference. The reason I don't test for it on exams, honestly, is because usually like 2 people ever do this correctly. And usually, even if you don't do this part correctly, you end up getting the graph anyway. So it's just, I got tired of taking off so many points for it. It's helpful. It's not completely necessary. I will show it though, just to give you more practice. We're going to find the y-intercept. There might not be one, but there might be. I mean, think about it. You could have a big giant vertical asymptote through the y-axis. You might not have a y-intercept. We're going to find some x-intercepts. Now, it's kind of weird that you might not have any. Normally, you have some x-intercepts. Not always with polynomials, but most of the time you did. You might not have any. You could have a big old horizontal asymptote right through your x-axis. Possible. However, your asymptotes are going to be extremely helpful to you. So if you don't have intercepts, it's okay. Find any vertical asymptotes by solving q of x equals 0, and then find horizontal asymptotes using that rule for finding horizontal asymptotes. You're going to have to plot some points here. For the polynomial functions, sometimes it was optional, kind of depending on what your graph looked like. Most of the time, you're going to need to plot a couple of points here. If you want to use your calculator table to help you compute those, that's fine. Use the information obtained previously to graph the function between and beyond the vertical asymptotes. So wherever your asymptotes are, you should have a function that covers the area to the left of your asymptote, to the right of your asymptote, and in between the asymptotes. And if you have more than one asymptote, make sure that any area between them is graphed. Don't leave anything blank, or you'll lose something. Number 11. Okay, this is a very important example. Number 11. G of x equals 4x divided by x squared minus 36. Okay, so the first thing we were going to do was find symmetry in the graph. I'm going to tell you right away there's no symmetry. Some of you got really good, actually, at being able to compute f of negative x. And when you did so, you realized that if you had powers that were even and odd, that you were not going to be able to get any sort of symmetry out of that. If you would like to see me do this, it's probably a good thing to go over again. We can talk about g of negative x. A lot of us did not do well on this part of our last exam. Everywhere you see x, replace it with negative x. And then simplify. So in your numerator, you're going to have negative 4x. And then in the denominator, negative x times negative x is positive x squared. So we are not going to have any y-axis symmetry. However, sorry, I misspoke earlier when I said there would be no symmetry. I meant to say that there would be no y-axis symmetry. There definitely is some symmetry in here, but I just feel like origin symmetry, even if it exists, isn't that helpful for when you're graphing the function. It's much harder to actually use a point with origin symmetry to place it on the other part of the graph. To figure out whether your function is odd, oh, by the way, we did not conclude here. Okay, so your g of negative x does not equal g of x. However, we can now determine whether negative g of x is equal to g of negative x. So we'll do that by taking negative g of x. When you're taking the negative of a rational function, you can choose where you're going to put the negative sign. Most of the time, it's most helpful to place it in the numerator. You can also put it in front of the function, whatever you think is best. So when you're taking negative g of x, you're going back to your original, and I don't know, I'll just put the negative in the numerator. I always have students ask me, why did you only put the negative in the numerator? Shouldn't there also be one in the denominator? Remember that for a fraction to be negative, you only want either the numerator or the denominator to have the negative sign. If both of them had the negative sign, then it's not negative anymore. So if you want to make it negative, you got to put one negative sign there. Now, the good thing is you can see by looking above that negative g of x is actually the same as g of negative x. So we have an odd function with origin symmetry. I guess in a way that's kind of helpful, because at least when you get done graphing your function, you can flip it upside down and make sure that it looks the exact same. And if it doesn't, you'll know that you didn't graph it properly. All right, any questions about the symmetry? Okay, all right. So that was symmetry. Find the y-intercept, if there is one, by evaluating f of 0. You're not going to get much out of this, so we'll call it g of 0 in this case. G of 0 is 4 times 0 divided by 0 squared minus 36, which is just 0 divided by negative 36, which is 0. So that's something. I guess it's better than no y-intercept, because officially you have a point on your graph right now. So there's your y-intercept. Number 3, find x-intercepts by solving p of x equals 0. I don't want you to think like, oh gosh, what am I supposed to do here? Is it p? Is it q? Remember that if the denominator of your function is 0, that's where you're going to get vertical asymptotes. If the numerator of your function is 0, that's where you're going to have your x-intercepts. Because if the numerator is 0, 0 divided by a number is 0, and you'll get your function to be equal to 0. So to find the x-intercepts, we're going to set g of x equals 0. Which means that we're officially looking at when the numerator is equal to 0. So really, it's the same process that we use to find x-intercepts for polynomial functions. But in this case, in order for our rational function to be 0, we need the numerator to be 0. Now, if that's the case, x equals 0. So not super exciting because we already have a y-intercept at 0, 0. So all this is saying is that we have an x-intercept also at 0, 0. So nothing too groundbreaking there. When you're graphing your rational functions, however, a lot of the important stuff is not going to come from your point plotting and any intercepts that you have. With polynomials, your intercepts are major. With rational functions, the asymptotes are major. So let's go ahead now and work on number 4. Find any vertical asymptotes by setting the denominator equal to 0. Now remember, before you do that, you want to make sure that you don't have any common factors in the numerator and the denominator. So in this case, there's nothing that we can cancel out. So we can go ahead and set our denominator equal to 0, and whatever values we get, those will represent vertical asymptotes on the graph. Vertical asymptote is VA for me. We're going to find that, find those vertical asymptotes by taking our denominator and setting it equal to 0. Now, if you want to use the square root property, fine. If you want to use the difference of two squares, better, in my opinion. And you'll get x equals -6 and x equals +6. Now, notice how I'm labeling everything as I go through. I would highly recommend that you do this. G of -x, negative g of x, g of 0, we have a y-intercept. We talked about finding the x-intercept, and then vertical asymptote. You don't want to lose all this information because it is a lot and it can kind of meld together. Before we plot our vertical asymptotes, which I think is a good thing to do as soon as you find them, does anybody have a question here so far? All right. So go ahead and plot your vertical asymptotes. I like to do that right away just because it sort of gives me a better idea of what's going on in my graph. So one of them is going through x equals 6, and the other one is going through x equals -6. Now, the next thing we're going to do is find the horizontal asymptote. Your function, we can rewrite, this is at least the way I'm going to do it, by using that 0 placeholder. Then I don't have to go back and look at the rule. We'll rewrite it so that we have a lead coefficient of 0 in the numerator. And then this will tell me that my horizontal asymptote is at y equals 0. 0 divided by 1 is 0. Now, it's kind of hard to graph an asymptote that's sitting on the axis because it's hard to see it. You've already got a line there. What I would suggest, because you do want to make sure that it's on there and that you notice it, it might look like it's coming off of the axis a little bit. That's okay. Just make sure you can see it and make sure I can see it. All right, so we've got the asymptotes. Your next instruction is to plot at least one point between and beyond each x-intercept and vertical asymptote. You have a point at 0, 0. That was your x-intercept and your y-intercept. What you don't know now is what's happening beyond that. Now, in the middle, you have these two vertical asymptotes. So the middle of your graph has to be doing something where it's approaching the asymptote either sending f of x towards infinity or sending f of x towards -infinity. It has to somehow follow these asymptotes. Your question is to figure out what exactly is happening in the middle of this function. So if I were you, I would pick a value not too close to the intercept, maybe in the middle somewhere, just to get an idea of where it is. Because you know if you get a value up here, then it must be the case that your graph is following this behavior that f of x is increasing as x gets smaller. And then if you get a point that's up here, you'll know that, okay, it must be the case that I'm graphing also f of x, sending f of x to infinity in this piece of the graph. So maybe pick a value like, I don't know, 3. and then see what you get. Now, if you really get stuck, you can technically, there's nothing I can do to stop you from putting this into your graphing calculator and looking at the table to verify these points. However, I'm going to be checking for all of this work on your test. So if all you do is pop this function into your graphing calculator and then just copy the graph down on your test, you're going to get no points for it. I'm expecting to see all of this work. Anything that I label, if I don't ask you for symmetry, that's fine. Then you don't have to include it. But as far as finding the y-intercept, you've got to show me the work for that, not just 0, 0. You have to show me g of 0 equals, you know, x-intercepts. Show me your numerator equals whatever it equals. I have to see this work. So if you just pop this in your calculator to check it, fine. Nothing I can do about that. But you do need to show me some work. Show me what values that you're plotting on your graph. So don't just give me a value somewhere up here or somewhere down there. Show me what you checked. Show me what the point is. All right. So that being said, 4 times 3 in the numerator, 3 squared minus 36. You end up with 12 divided by, and honestly, it doesn't even matter that much what the point is, because now you know what's happening here at this point, because f of 3 is negative. And if f of 3 is negative, then you know that you've got a point that's happening in the bottom piece of that graph underneath the x-axis. So let's see. Negative 12/27 is a really, really, really small value. So that means that when you're at 3, you're at like negative a half-ish. It's do the best you can. If you don't like that point and you're like, ooh, I'm having a hard time even graphing this at all, this is weird, it's such a small value, that's fine. Look closer at that point then to the asymptote. Look at something like f of 5. (25 minus 36, negative 11). Okay. Then at least you'll get something that's a little bit over 1 in this case. 11 goes into 20 one time with 9 left over. So it's like negative 1.5. So you can include those pieces. Now, if you're savvy about your origin symmetry, you can use that to pop this up over here. If you're not sure, feel free to, again, check the values for the negative pieces here, like for instance, f of -3. However, know that when you do that in the denominator, you're still going to get a negative number, but now in the numerator, it's also going to be negative. So you're going to get something positive. So it must be the case that you would end up getting positive 12/27. So you're going to see this same behavior come up over here on the left. I am going to ask you to label these on your test. I'm going to, well, for those of you who have the capability of printing it out, you're going to have a nice big graph. But other than that, if you're making your own graph, you're probably not going to make it this tiny. So yeah, please make sure that you're labeling your information. Okay, so go ahead and connect these with the nice smooth curve. I'm going to actually send this up to my asymptote in a second. For now, we're just going to make a nice smooth curve, and it's very rapidly going to switch directions as it approaches the asymptotes. So that's what's happening in the middle. Does anybody have a question so far? Now, the only thing left is what's happening on the sides. Now, notice that you can only have a few different types of things happening here. You've got an asymptote here. There's only one way that you can come out of this asymptote, either from up this way or from down here. You cannot do anything else. There's no other way that you can come out of here. It must be the case that you must be either heading down like this or heading up towards the asymptote that way. Same idea over here. There's no way that you can approach from the right anywhere other than from infinity and then down, or from negative infinity and up. So all you need to do is find 1 point. And when you find 1 point, you'll know exactly what's occurring here. Let's go ahead and maybe look at something. Let's see, we have an asymptote at 6. So if you want to look at 7, that might be a good one. You might prefer 8. Well, actually 8 will probably be a little bit of a smaller value. Let's choose 7. So 4 times 7 is 28. 7 squared is 49. So you have 28 over 13. So this is 2 and 2/13. So it's just a little bit more than 2. The most important thing, though, is that it's a positive value. So that means that whatever's happening on your graph is happening above the x-axis. So if we're talking about 7 and then a little bit more than 2, it's a point that's right about here. And that's all you need. You are going to be approaching this horizontal asymptote as your values of x get larger and larger and larger and increase towards infinity. Now, even though you cross the horizontal asymptote in the middle, you cannot cross it as your graph heads towards the end. You must approach the asymptote. It is the end behavior of your graph. And I guess that origin symmetry was actually pretty useful because you know that you want to be able to see the same exact image when you flip your graph upside down. That means that when you flip it upside down, you want to be able to see this piece over here. I know some of us have a hard time visualizing that. So if you have a hard time with the origin symmetry and you don't see that, that's fine. Plot f of -7. Get a point over here to the left of x equals -7. And then you'll see something similar occurring just in a negative value. And then you can plot that down here. So -2, a little bit more than -2. Looks like that. And it must be the case that we have to approach these asymptotes. That's the key. Remember, these are functions. They have to pass the vertical line test. So don't do something crazy where this curves back out or something. It must approach the asymptote. It still has to pass the vertical line test. All right, questions on your rational function? Okay, let's talk about the slant asymptote. What I like about the slant asymptote is it kind of brings everything back together again, talking about long division. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So it always has to be exactly 1 more. In general, if f of x equals p over q, p and q have no common factors, the degree of p is 1 greater than the degree of q. We'll find the slant asymptote by dividing q into p. So we'll do that in example 12. Find the slant asymptote, if any, of the graph of the rational function. So notice here that you're being given a function where the degree of the numerator is 1 more than the degree of the denominator. If that is the case, then you have a slant asymptote. You just need to figure out what is the value of the slant asymptote. To do that, you're just going to use long division. Now, don't be all confused about, wait, divide q into p, which one is which? Think about any time you have a division problem, you're taking the numerator divided by the denominator. So I'm going to kind of move my work over here. I think we need a little bit more space. X squared plus 16. Well, I forgot my plus 0x. Divided by x. Now, the non-remainder portion of this quotient is going to be our slant asymptote. So x squared divided by x is x. We should be pretty good with our long division by now. X times x is x squared. Now you don't have a binomial that you're dividing by in this case, so you don't need to worry about multiplying by anything else here. You're going to subtract, bring down anything you have left. Sometimes simpler problems seem harder just because I don't know, there's just not a whole lot going on in them. Now, you'll know you're done because if you take 16 and divide it by x, you just have a variable in the denominator. So officially, your slant asymptote is just going to be y equals x, the non-remainder portion. Your remainder doesn't actually factor in here to your slant asymptote. So there's your slant asymptote. Y equals x. I wanted to also, when I was looking at this, I was looking at C. Don't be thrown off by C, because remember that even if you were to write this quotient the way that we wrote them back in 3.3, you would have written this as x plus 16 over x. You would not have written it as x plus 16. So your slant asymptote is the non-remainder portion of the quotient. Also notice that D is the option for no slant asymptote. As long as the degree of the numerator is 1 more than the degree of the denominator, you're going to have a slant asymptote. Any questions on 12? Number 13. You have a situation, once again, where the degree of the numerator is 1 more than the degree of the denominator. In this case, and by the way, if you're like, wait a second, now I'm confused, which one's which? If you put your placeholder here in the denominator as 0x squared, you would be able to clearly see that you don't have a horizontal asymptote. You have a slant asymptote. So go ahead and use your long division. Oh, actually, you know what I was just thinking here? Let's see, negative. Oh no, that wouldn't work in this case. Never mind. We must use long division. If you can, I was going to say, if you can factor this and then cancel between the numerator and denominator, then you wouldn't even need to use long division. But this one's not factorable. So go ahead and take your numerator divided by the denominator. So x squared divided by x is x. Multiply your x by the x plus 6. And subtract. Negative 6x minus 6x is negative 12x. Be careful with those coefficients. I know so many of us see this minus 6x plus 6x and we want to say, oh, 0, we're done. Be very careful. Make sure you're using that subtraction. Negative 12x divided by x is negative 12. Negative 12 times x is negative 12x. Negative 12 times 6 is negative 72. Subtract, and at this point you can stop because who cares what the remainder is. That means your slant asymptote is y equals x minus 12, which is C. If you are not sure even what a slant asymptote is, you might see one on your graphing homework. Actually, you know what? You might not see one on your graphing homework. A slant asymptote, similar to a horizontal and a vertical asymptote, guides your graph. X minus 12 is going to have a y-intercept at negative 12. And y equals x is going to have a slope of 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you're going to go up 1 over 1, up 1 over 1 until you get all the way back to 12. So what this means is you're going to have an asymptote that goes through the line y equals x minus 12. Now, a lot of times you're not just, actually, I can't think of an occasion where you would just have, yeah, it's not possible that you're going to just have a slant asymptote. You're always going to have a slant asymptote and then a vertical asymptote. So in this case, you would also have a vertical asymptote at x equals negative 6. Now that's way over here. But what you would see occurring is you would see a portion of your graph either up here and down here, or you would see a portion over here and over here. So it kind of depends on what else is happening in the problem. If we have time, we'll graph this, but I don't think we're going to have time today. But you can plot some points and you'd very quickly discern which pieces you'd actually be graphing there. Does anybody have a question about that? I want to make sure that you understand what we're doing here. Okay. Wonderful. Number 14. 8x squared divided by 4x squared plus 6. I'm looking for a situation where the degree of the numerator is 1 more than the degree of the denominator. Do I have that? The degree of the numerator is the same as the degree of the denominator. So in that case, we would just say no slant asymptote. It must be the case that your degree of the numerator is 1 more than the degree of the denominator. Maybe I'm going to underline that because I want to make sure we understand when we'll have a slant asymptote. Okay. Number 15, I don't want to go over in class. It's just an evaluate the function. I'll give you the answer so you can check it, but that's really not something I'm worried about you being able to do, evaluate rational functions. You're just plugging in 50 for x, but number 16 we will go over. A drug is injected into a patient and the concentration of the drug is monitored. The drug's concentration, C of t, in milligrams after t hours is modeled by C of t equals 5t over 2t squared plus t. What is the horizontal asymptote for this function, and describe what it means in practical terms? If you're looking for a horizontal asymptote, set yourself up into a situation where the degree of your numerator is the same as the degree of the denominator. Insert that placeholder. Or go back to your rule, that's fine too. And you end up with y equals 0. Remember that y is really C of t in this instance. If your horizontal asymptote is y equals 0, that means that C of t is eventually going to head off to 0. C of t is the drug's concentration. Does anyone want to unmute or chat me up and tell me, what does your horizontal asymptote mean in this situation?
As time goes on, the levels of concentration will decrease and decrease and decrease, but never reach zero?
Yes, you're right. Yes, thank you. Very good, Beth. I'm really glad that you said that it's never actually going to reach zero, which seems a little bit odd. You would think that eventually at some point it would all just completely die off. But I mean, I'm sure you end up with just this minuscule, very teeny tiny amount that really would never be measurable in your system. I guess that would have to be the case here. I don't know though, because I'm not a physician. But yeah, officially, that's what your horizontal asymptote would be representing. After T hours, or after a certain number of hours, C of T approaches zero. That means that the concentration wanes towards zero as time increases. And if you wanted to, you could even plot this function into your graphing calculator. Don't use T, use X. If you try to use T, your calculator is going to get confused. But if you try to enter y equals 5x over 2x squared plus 2, you should be able to see how infinitesimally small that value is going to get as T gets larger and larger. I think someone's calling Mom. I don't know. I could be hearing phantom moms. No. All right. How about, I was going to graph a different rational function with you guys. Would you like to graph this slant asymptote function? No? Not at all? Okay. That's fine. We'll graph a different one. It's like I hear a child calling for me. Okay. The one that I thought we should do was I'm gonna turn to the back here. I don't know if you guys have a back sheet on your notes. Do we have a back sheet? I have no idea. I'm very stressed out right now. No back sheet. Okay. Do we have an extra sheet of paper? Don't just say no because you want this to be over with. No. Yes. Okay. How about this? I'll go through this example. And then if you really want me to, I can post it later if you were like, oh my gosh, I can't find paper and I couldn't put this down and I really wanted to. Because, I mean, we have like 7 minutes. I would hate to waste that time that we could have had graphing rational functions. It'd be terrible. Okay. Let's graph this function. If you have somewhere to put it, or if you have a piece of notebook paper close by, f of x equals 3x minus 3 divided by x minus 2. This one is a little bit of a simpler rational function, but I still think that it's really instructive. Okay, so thinking back to our instructions, we were talking about symmetry. And again, I probably won't require this of you, but I think it's always good practice to look for symmetry because we're so bad at evaluating f of negative x. Sorry, maybe not all of us are so bad at it, but I've found that students in general are not very good at that. Okay, so negative 3x minus 3 divided by negative x minus 2. Also, I think it's really good just to be able to work with these rational functions and all their negative signs. Okay, now I think we can clearly see that this is not equal to f of x. So we know it's not even. So now we'll find negative f of x. Now, when you find negative f of x, you're going to, like I said, you can put the negative wherever you want it to go. But notice that you don't have a negative in front of this function. So if you want to try to match this function, I would put the negative in the numerator. Now it's got to apply to both terms in the numerator. So don't just pop a negative in front of the 3x. It's got to be negative of that whole numerator and then divided by x minus 2. And that gives you negative 3x plus 3 divided by x minus 2. Negative f of x, oh sorry, there's our f of negative x, is not the same as f of negative x. Now, you could move your negative sign around a little bit and try to get it to match, but both of the terms are negative here in the denominator for f of negative x. For negative f of x, only one of them is, so you're not going to get these to match. So it's also not odd. So there's no symmetry. The next thing we'll do is look for a y-intercept, then we'll look for an x-intercept. So the y-intercept is f of 0 which is negative 3/2. So you're going to have a point on your graph at 0 and negative 3/2. I'm going to zoom this out a little bit. Oh, you know what? Sorry, I missed something. In the denominator is negative, it's positive 3/2. See that one little thing and I would have started to graph it and been like, what the heck? This doesn't make sense. Something is wrong here. All right, x-intercepts, we are going to take the numerator and set it equal to 0. And when we do that, you'll get x equals 1. So we have a point at 1, 0. So this is kind of nice because in this case, we at least have 2 distinct points that are going to be sitting on our graph somewhere. We are going to now look for our vertical asymptote. The vertical asymptote will be when the denominator equals 0. And that's going to be at x equals 2. And then a horizontal asymptote. Well, in our case, the degree of the numerator and the denominator are the same. So we're going to take the ratio of the lead coefficients. 3x divided by x is 3. Ay, ay, ay. I'm teaching a class now. Can you come back later? Okay, I'll be down in a minute. My debate crew is here. I know you guys are like, okay, wrap up. Okay. Y equals 3. Okay. Y equals 3 is my horizontal asymptote. Oh, yes, ratio of lead coefficients. All right. We're going to plot all of this information on our graph. You'd think my husband would be telling him to not come up here. Like, what is he doing? Okay. So we have a horizontal asymptote at y equals 3 and a vertical asymptote at x equals 2. And the nice thing is we already have some points. I know I have an x-intercept at 1, 0. And I have a y-intercept at 0, 1.5. And this is good because this will end up following the direction of my asymptotes. I don't even need to plot anything over there. Now I will plot a point at maybe x equals 3 just to get a y value over there. Let's see, that's 6 over 1. So when x equals 3, y is 6. And then we're going to see the same behavior occurring up here. So there's only one way that I can approach these two asymptotes, and that's by curving the graph this way. All right, that is all. Your My Math Lab homework from 3.5 is up. It's available, 3.5 part 2. You can enjoy that. If you'd like to see me graph the slant function, that's fine. We can do that too. And well, actually, I was probably going to go find my debate team. But if you want to see the slant function graphed, email me and I'll send it to you. I'll graph it, send it to you. Or you can always graph it in your graphing calculator. Your graphing homework is 3.5. I put the assignment up on D2L. I will double check what the numbers are for you. Ugh, it never lets me do this. It is on page. Assignments. Graphing homework. Page 427, it's number 58, 60, 64, 70, and 76. So 5 of those that I would like for you to do by hand. I think they will really help to prepare you for your exam. And that is all. If you have questions, email me. If you really want me to put a review assignment on my math lab, I will. But last time I spent a long time putting it together, nobody did it. So I don't want to waste my time if you're not going to do it. But if you are going to do it, email me and I'll put one up there. Have a good weekend. Email me if you have questions. And your test is on Monday. I'll send an email about the test too. Bye. Enjoy the debate. Go watch the debate. It'll at least be entertaining, we hope.